Hi, I'm John McMillan, and welcome to today's webinar demonstrating signal integrity analysis. Did you know that lack of SI validation is one of the key reasons why designs fail in the field? That's why 75% of best-in-class companies implement signal integrity analysis. In today's high-tech PCB designs, nearly every PCB can benefit from signal integrity simulation and analysis. In fact, it's not a luxury, it's a critical step in the product design process. SI analysis not only ensures that design constraints meet product performance requirements, but also prevents you from over-constraining your PCB designs and alone increases product success by more than 18%. So, to show you how accurate and easy to use signal integrity analysis and PADS Professional can ensure your product will meet its performance, time to market, and cost goals, I'll turn this webinar over to one of our technical marketing engineers, Shivani Joshi, to demonstrate how. Shivani?
Thank you for the introduction, John, and welcome everyone to the PADS Professional Signal Integrity Analysis webinar. In this age of modern electronic design, signal integrity has become an essential factor. Increasingly fast edge rates in today's integrated circuits cause detrimental high-speed effects, even in PCB designs running at low frequencies. Analysis at every step of the design process has become essential in producing quality boards with less rerun time and cost. With HyperLynx signal integrity in the PADS Professional flow, analysis can be done quickly and simply. With HyperLynx, you can address high-speed PCB problems throughout the design cycle, beginning at the earliest architectural stages and moving through post-layout verification. In this video, I'll cover some of the key functions within HyperLynx's pre-layout environment, LineSim, and its post-layout environment, BoardSim. Starting in PADS Designer, you can export individual nets to simulate in a pre-layout environment. Here, I'm delving into my battery protection block and selecting my desired net for simulation. With a quick right-click export, I can review the net and quickly export to HyperLynx LineSim. In LineSim, I can see that the driver model hasn't been selected. Double-clicking this part will open the Assign Models dialog where I can see all my drivers and receivers for this net and assign its model. For the selected part, I will select my IC model from my desired library, device, and signal or pin. I'll also want to assign the IC as either my input or output based on what I'd like to simulate. Here I've selected output. The next step is reviewing my transmission line. Using this dialog box to edit transmission line properties, I'm able to choose which transmission line type to simulate for the selected region. I can choose from StackUp, Microstrip, cables, and many more. The Values tab can aid in my layout decisions as well. Choosing the layer I'd like to route on and the length and width of the trace, I'm able to quickly review the changes in my electrical properties to make sure I'm staying within my requirements without any guesswork during layout. Another factor that can help before layout are adjustments to my board StackUp. The StackUp editor allows for easy planning and shows how changes in physical properties, such as layer thickness and material, changes the electrical properties like characteristic impedance. I can plan according to impedance targets, and HyperLynx can calculate the appropriate width for that layer. For differential pairs, I can choose to keep the separation constant and solve for trace width, or vice versa. You can solve for both by producing a width versus separation graph to aid in optimal value selection for your target impedance. This is an ideal tool for SerDes and DDR nets, which can be more sensitive and need additional planning. HyperLynx also simulates coupling regions to define how two or more traces are coupled electromagnetically. I can select two nets from my schematic and bring them into LineSim as I did before. To visualize the coupling region, select two transmission lines and couple them. Here, you can move the trace to different layers in your StackUp, but I'll leave both lines on the top layer and name this coupling region as such. Note that as the physical adjustments are made, the characteristic impedance is affected. The Field Solver tab calculates the electric and magnetic fields associated with both transmission lines. The propagation can be switched to show differences between common and differential modes. To minimize reflection, HyperLynx in Pads Professional provides a convenient way of quickly terminating nets. The Terminator wizard is used to improve signal integrity properties for nets in your board or schematic design by finding optimal termination component values. The wizard makes suggestions for improving the performance of the net, including adding termination, changing the value of existing terminating components, or adjustments to net length. In this case, the Terminator wizard first determines that the net is too long, suggesting a driver to receiver value of less than 3.488 inches. It asks you to consider a few other options to improve the net's signal integrity, including adding a series terminator, rerouting to reduce the net length, or choosing a different driver. Here, I'll add a series resistor as suggested by the wizard. To calculate the best value for this resistor, running the wizard again with the 0 ohm resistor will prompt the Terminator wizard to suggest an optimal resistor value, 48.7 ohms. The ringing has drastically changed without any personal calculation, as all possible solutions were provided by the software. After the board has been routed in Pads layout, I have another critical opportunity to analyze my design. I'll bring the entire board into HyperLynx BoardSim for post-layout analysis. All routed and unrouted traces seamlessly import, and now I can see how my board layout has affected these nets and the design as a whole. I'll again select my battery protection net that I simulated in LineSim and add the appropriate IC models. With the same user interface as before, I can select the library, device, and signal that I want for this net. Now to go through some settings. I must ensure that the software recognizes differentially paired nets correctly, so it can simulate them correctly. You can specify differential pairs for a design by selecting or typing the net names. Note the status column displays invalid if the software does not support this pairing. For example, this can happen if the nets do not connect to pins on the same component. Before starting analysis, we can choose to enable some coupling options. Go to Setup, Coupling Settings, and use this dialog box to specify trace, package, and area fill coupling settings. Selecting coupling thresholds opens a dialog box where I can choose the constraints for crosstalk simulation with either geometric zone or electrical estimation. Here, I'll keep it with electrical. To demonstrate signal-to-trace coupling, I'll first select 3 nets, then enable the signal trace coupling option. Automatically, a 4th net is selected. With my nets selected and coupling enabled, I can run the General Batch Wizard for detailed analysis and quickly predict which nets are likely to suffer the most crosstalk. I'm going to run signal integrity and crosstalk simulations on this run, then continue with this wizard. I can choose to select different nets for analysis or the ones I've already selected in my design. I'm going to focus on just the selected nets for now and continue. The simulation settings allow me to choose precisely what I want analyzed, including IC modeling corners, fast strong, typical, and slow weak. I can also adjust the coupling settings and thresholds here. I've set these before, so I'll keep them as they are. I can choose a default IC model for the analysis and change this after the design. Since I don't have many nets selected, I'm choosing to simulate all driver-receiver cases in a round-robin fashion, meaning one IC will be made a driver while the rest are made receivers. Then the simulation starts again with the next IC made a driver and so on until all cases are exhausted. The crosstalk settings allow for setting the aggressor net stimulus. Finally, in the reporting options, I can choose how to deliver results. These reports will be saved for easy analysis review later on. Once I run the batch analysis, I see that I have failed signal integrity and crosstalk parameters for all selected nets. By clicking on the Fail link, I am directed to more details about these nets' failures. I see that some didn't meet signal integrity requirements and some had excess crosstalk. With further inspection, I see that only the crosstalk net met signal requirements, but failed crosstalk limits, while some of the motor nets had the opposite results, or failed both requirements. More details follow in the All Crosstalk Simulations tab, where all cases of victim and aggressor nets were exhausted, even pointing out where net coupling was not a factor. Going back to the design in BoardSim, I can use the Quick Terminator to improve my signal integrity issues provided in the report. Quick terminators are special components that allow you to experiment with terminations that are not currently on your board design by adding temporary terminating components. After some adjustments, I'll rerun the batch analysis wizard to see that all signal integrity and crosstalk restraints were met. Taking a look at the design's clock net, I can see there are other ways of analyzing and optimizing my design. I see that the clock net couples with the net above, so I can assume there may be ringing issues in my design. I'll set the clock net driver as stuck high to see the effects. I'll run the oscilloscope to see that there is, in fact, a bit of ringing on this trace. Using the handy measurement tools, I'm able to quickly measure the overshoot and undershoot of this signal and go back to address these design concerns. In the oscilloscope view, I'm also able to quickly simulate with different IC coupling speeds without having to go back to the BoardSim view. I can also simulate multiple scenarios with the interactive sweep feature. In the Sweep Manager, I am able to select a range of simulation cases to best help me with my design constraints. In Stack Up Layers, I can simulate across a range of layer thicknesses, dielectric constant values, or loss tangents for any layer. A sweep of different power supplies and buffer models is also available. Here, I'll sweep across my IC operating parameters to examine the signal at each process corner: fast, strong, typical, and slow, weak. The simulation cases show a detailed view of what's to come once I run the sweep analysis. I can easily hover over each waveform to see which case is simulated and analyze from there. In HyperLynx, you can identify board design changes that solve specific signal integrity problems by selecting the problem nets in BoardSim and exporting them to LineSim. Signal nets exported to the schematic design can include trace properties, associated pins, IC model assignments, and more. I want to make sure I'm taking the selected clock net as well as the coupled segment so I can address the issues fully. This net looks very different compared to the simple driver, transmission line, receiver that we could see in BoardSim. This schematic breaks down the transmission line to show every section that is coupled and uncoupled to aid in pinpointing a solution. From here, I have the ability to test what-if scenarios by making physical and electrical changes and simulate as before. In this demonstration, I've shown you how signal integrity analysis has enabled me to efficiently analyze, solve, and verify critical nets from schematic design through final layout verification. From accurately modeling trace impedances and coupling to recommending optimal termination strategies, you'll be able to address design parameters before even starting layout. Keeping designs in check post-layout is just as easy with crosstalk and signal integrity analysis reports and quick simulation sweeps to ensure all facets of the design are behaving properly. With fast, easy, and accurate signal integrity analysis results in PADS Professional, designers can efficiently manage rule exploration, definition, and validation, all enabling shorter time to results for PCB designers and signal integrity specialists alike.